Okay, so this is chapter 13 homework. All right, first one, a mass oscillates on a spring with a period t and an amplitude, so A. So we know t and we know A equal to, let me see, A equal to 0.48 centimeter. The mass is at the equilibrium position, x equal to 0, at t is 0. Okay, so this is called initial condition. It's very important. And is moving in the positive direction. Okay, where is the mass at the times? Okay, those are different times. All right, so we discuss the position time graph equal to A cosine omega t. That's what we have. Actually, it's also A cosine 2 pi over period t. That's what we learned in class. Okay, so the curve should look like that. X, t. Okay, so that is the curve we learned. The point here is this. For this curve, when t equal to 0, you see, the position actually is at amplitude. Okay, and then object will move, you see, displacement decrease, right, to 0, so move in the negative direction. All right, but this is different from this initial condition. So this tells you that at x equal to 0, t equals 0, x is 0, and is moving in the positive direction. So definitely it's not this curve. However, if we move this curve, shift to right by pi over 2, okay, then you get here this, right? Shift to right by pi over 2. You see, when x equal to 0, and when t equals 0, x is 0, right? And then move in the positive direction so that next moment displacement increase, right? So just like that. All right, so this is the right curve. Well, the curve, if this is the right curve, then the equation, we have to modify the equation. So here, if you move to the right by pi over 2, so the whole thing will change by this. 2 pi over t, move to right by pi over 2. Okay, so this is the equation. Okay, so equation here, also we know A equal to 0.48 cosine 2 pi over t minus pi over 2. Okay, so this is the equation. All right, now give you a time, then you know the position, you know the displacement. So t equal to, time equal to t over 8, right? So A, what is the position? X, t equal to t over 8, right? So plug in 0.48 cosine 2 pi over t. Now you substitute t by t over 8 minus, okay. All right, so this is 0.48 cosine. T and t cancelled, right? So you have a, then minus this. 48 cosine negative pi over 4. So pi over 4 is basically 45 degree, right? So this equal to 0.48. You use your calculator, you see this is square root over 2, okay? So this will be 0.24. Let me see. Okay, let's use calculator. Times 2. Okay, so 0.339. Okay, so that's object after t over 8. Same idea. You will do t over 4, t over 2, and 3 over t. Actually, what's the t over 4? You see, this is one period, right? T over 4 is here. So this is half period. So this is t over 4. So t over 4 should be the amplitude location, right? T over 2, well, t over 2 is here. You see 0. And 3t over 4. 3t over 4 actually is here, right? So, well, you don't have to do this anymore, right? So just so you can put the answer here. T over 4 is 0.48. T over 2, 0, negative 0.48. The first one, you have to make a calculation. All right, so that's the first question. Second one, a mass attached to a spring oscillates with a period of 3.35. So what do we know here? It's a period of equal to 3.35 seconds. That's a period. If the mass start from rest at equal, so this is x, right? Start from rest at this. Okay, which means you start from the extreme location. All right. At t equals 0, where is it at this time? Okay, so this one, we can tell this actually is, okay, so this actually is, you see, you start from here, start from 0 point, so we can tell 0.044, so A start from positive A, right? A equal to 0.0044 meter at t equals 0. So this is t, this is the x, start from here, A. Okay, where it is at t equal to this. Okay, so we can tell this, actually we can just use a standard equation. So x t equal to 0.044 cosine 2 pi over tt. That's good enough, right? So you can substitute t by 3.35. So this equal to 0.044 cosine 2 pi 3.35 t. Okay. All right. So where is the object? Well, you just substitute this one. Okay, so substitute by this, right? So t equal to 6.37. So plug 6.37 to here. Then you can figure out what is your x. Remember, you have to use radian. This is radian. When you use a calculator, remember to use radian. So this is radian, not degree. Everything here is radian. All right. That's the first question. If the mass moving in the positive, is the mass moving in the positive or negative direction at this? Okay, so whatever it is, right? Okay, so move in the positive or negative. Well, let's see. You look at the velocity. If velocity is positive, then positive direction. Negative, then negative. So what's the velocity equation? This is xt, vt, okay, equal to negative. Remember in class we talk about a omega sine omega t, right? So this is equal to negative a. A is we don't know a, right? So 0.044. What is omega? Okay, omega equal to 2 pi over t. Remember the omega, right? 2 pi over 3.35 sine. Okay, so 2 pi over 3.35 t, then you 6.37 plug in. Okay, so you calculate if the velocity is positive, then it is in the positive direction. If it's negative, that is negative direction. Okay, so move in the positive or negative direction. This asks you about the velocity direction. Okay, so just use the equation to figure this out. Motion equation. All right, next one. Let me erase all this. Okay, next one. An object executing simple harmonic motion has a maximum speed of this. So V maximum speed equal to 4.1 meter per second, and the maximum acceleration. So A maximum equal to 0.85 meter per second square. Find the A amplitude and B the period of the motion. All right, so from the equation, well, we know equation. So xt equal to A cosine omega t, right? Okay, so that's the equation. That is a position. So what is the velocity? Velocity equal to negative A omega sine omega t. Acceleration at equal to negative A omega square cosine omega t. Okay, so maximum velocity means, you see, maximum, right? Which means A omega. Well, because this is a sine curve, right? So if you look at the velocity is a negative sign, right? So this is the velocity curve, right? So this is a maximum velocity, right? So this is maximum. And what is this value? This value is A omega. Then you have a sine function. Okay, so A omega equal to 4.1 meter per second. And ask you, and also tell you maximum acceleration. So A omega squared, this is maximum acceleration, right? So A omega squared equal to 0.85, all right, meter per second square. Then ask you amplitude and the period, right? You see A omega equal to 4.1, A omega squared equal to 0.85, right? You see? Then A omega squared over A omega. So basically this is maximum acceleration divided by maximum speed. So this you see. Let me think. Okay, so okay, so reverse way. So A omega equal to 4.1. This give you omega equal to 4.1 over A, right? And then you plug omega into this equation. So A omega square, right? So 4.1 over A square equal to 0.85. Okay, so from this equation, you can figure out A, right? So let's see. So A times 4.1 square, A square equal to 0.85, right? So it's A cancel 1, so you put A other side equation, and then you can figure out, put this to another side equation. So A equal to 0.85. Okay, so that's A. And then the second one is period, right? So A and the period. So what's the period? Well, if you have A, you can figure out what is your angular frequency. And then period equal to 2 pi over angular frequency. Okay, so that's how you solve this problem. All right, so let me erase everything here. All right, let's look at the next one. Next one is this. A peg on a turntable moves with a constant tangential speed. Okay, so this is uniform circular motion with a speed 0.282 meter per second. That's a tangential speed. Let's make it a VT. Okay, tangential in a circle of radius. Okay, so we know that is radius 0.33 meter. This is uniform circular motion. Okay, so this is A, and this is the tangential speed, Vt. All right, the peg casts a shadow on a wall. Okay, so that's a shadow, right? Find the following quantities related to the motion of the shadow. So we know if you have uniform circular motion, then the shadow is simple harmonic motion. Okay, so let's see the period of the motion, right? Simple harmonic motion. So the period. Well, period actually is the same, right? So the when objects move one circle, then the projection or shadow will move one cycle. Okay, so that's the relationship. Okay, so uniform circular motion and simple harmonic motion. One circle of uniform circular motion is one cycle of the simple harmonic motion. So the period, so those two have the same period. So period for uniform circular motion is, you see, distance over time. Distance over, so this is time, distance over speed, right? Distance is one circumference, 2 pi a divided by speed. Okay, so that's a period. 2 pi 0.33 divided by 0.82. Okay, so that's your period. B, the amplitude. Okay, so what's amplitude? Well, we know amplitude is your radius, right? So A, so this is A, 0.33, that is amplitude. Okay, third one, the maximum speed. Okay, so what's maximum speed? Maximum speed actually is, you see, when object is here, turntable, right? Go this way. So the projection right here is all, this is the same. Right? So when you at the top or at the bottom here, this is the maximum speed of the simple harmonic motion. Okay. So this tangential speed actually is your maximum speed of the simple harmonic motion. Okay. Last one, the maximum magnitude of the acceleration. What is acceleration? We know acceleration A, centripetal acceleration equal to Vt squared over A, right? And the centripetal acceleration is your maximum magnitude, okay? Because you see, so this circle, right? So when object is here, okay, so this is your centripetal acceleration. You point to so the AC, right? And this is your acceleration for simple harmonic motion, okay? However, when object is here, you see, this is your centripetal acceleration. And at this moment, you have maximum acceleration for the simple harmonic motion. Okay, so centripetal acceleration actually is your maximum. Okay, so when objects reach here, right? So this is centripetal acceleration, but the acceleration of the simple harmonic motion is this. This is not a maximum one, right? When you are here, this is your centripetal acceleration, and there's no components in the horizontal direction. So here for the simple harmonic motion, object actually is at the equilibrium location. Acceleration is 0. So at extreme location, acceleration is maximum. Okay, so well, that is the answer, right? So this actually is your maximum acceleration for simple harmonic motion. So this question asks you about the relationship between uniform circular motion and simple harmonic motion. All right, number 5. 0.84 kg air cart. Okay, so we know mass equal to 0.84 kg is attached to a spring and allowed to oscillate if the displacement of the air cart from equilibrium is this. Okay, so you have displacement equation. 1.0 centimeter. Okay, so this is centimeter. Cosine 2.0, right? So this is actually the omega, right? So 2.0 s and t plus pi. All right, so this is the equation. So from this one, we know A equal to 10.0 centimeter, omega equal to 2.00. This is omega. Okay, the maximum kinetic energy of the cart. Okay, so this is A, right? We learned that we learned the energy, right? So at any given moment, the total energy, right? Total energy equal to 1/2 Ka squared at any given moment. This is your kinetic plus potential, right? And when do you have the maximum kinetic energy? Okay, when this is 0. Okay, so you have maximum kinetic energy. So maximum kinetic energy is the total energy. Okay, so this is just plug everything in, right? So you have A, and you don't have K. So you need K. So what is this K? If you know omega, then you know K, right? Because you have M and omega, right? So we know omega equal to square root of Km. Okay, so from here, we can derive that omega square equal to K over M. So K equal to M omega square. Okay, so from this, you know K, right? And then plug K into this equation, so you can figure out what is the maximum kinetic energy. Okay, so this is come from the total energy equation, right? So total energy equal to this. Energy equal to kinetic plus potential. When potential energy is 0, you have maximum kinetic energy. Okay. B, the maximum force acted on it by the spring. Okay, so what is the maximum force? Maximum force happens at when the object is at a location. Okay, so here is object, right? Mass, right? So this is your equilibrium location. This is your x equal to a, right? So when you are here, okay, so you have spring force here. Okay, so maximum force will be F spring force equal to K X actually is Ka. You have negative sign, but actually sign doesn't matter, right? So like ask about the maximum force. Okay, so this max force is K times A, right? You have K here, and then you can figure out you have A. You already have A. A is this, right? So you have maximum force. Remember, this is Newton. Okay, if this is Newton, and this is Joule, you have to turn everything into SI units, which means 10 centimeter equal to 0.1 meter SI units, right? And this is already SI units, okay? So, so that's you have to make calculation like that, right? So you have kg, yeah, kg. Okay, so plug everything in. You will make a calculation. Make sure you do everything carefully. All right, next question. Next question is, okay, is a 0.95 kg mass attached to a vertical spring. Okay, vertical spring. So this is a vertical spring. Okay, 0.95. Okay, so mass. So we know mass equal to 0.95 kg. Vertical spring of spring constant K. K equal to 130 Newton meter. Oscillates with a maximum speed of this. So V maximum equal to 0.45 meter per second. Find the following quantity related to the motion of the mass. Okay, so we have mass, we have spring constant. The period. Okay, so what's the period? Well, even you also like this, right? Up and down, the period is set. Okay, so we know angular frequency equal to square root of k over m. Period equal to 2 pi over angular frequency equal to 2 pi over this term, right? So equal to mk. Period is set actually for given spring and mass. B, the amplitude. Okay, so amplitude, you have same question, right? So this is the maximum velocity. Okay, so maximum velocity here is use the energy equation. You see, when object at equilibrium location, you have maximum kinetic energy, right? And when object at extreme location, you have maximum potential energy. Use this equation. Okay, well, let's see, what do we have? We have mass, we have k, right? You have this guy, angular, you have velocity, maximum velocity, then you can figure out a, okay? So that's magnitude. The magnitude of the acceleration, okay? Acceleration always happened at this, right? So it's basically it's a spring force, maximum acceleration, okay? Acceleration, same thing here, right? So it's a K A. Okay, so that's your maximum. So basically the spring force equal to Ka, right? You have K and you have A, you know the amplitude. Okay, so that is the maximum force. Maximum, acceleration, I'm sorry, acceleration, force, right? So this is the force, acceleration equal to force over mass, right? A equal to that. Then maybe the maximum force, okay, so this one is the maximum force, so this is the maximum acceleration. So you have to make a force over, so equal to Ka over m, okay? So that is acceleration, maximum acceleration. All right, so next one is 0.4 kg mass is attached to a spring with spring constant 0. From equilibrium position of the spring. Okay, so this mass attaches to the spring. Okay, so this is K equal to 26 Newton meter. This is mass, right? So this is mass. And release from rest at a distance 0.2 from the equilibrium location. So basically you start from here, right? So this mass, assume this x to 0. You start with x equal to A equal to 3.2 centimeter, 0.032 meter. Okay. Find the speed of the mass when it is halfway to the equilibrium. So basically ask you what's the speed here. So x equal to 1.6 centimeter equal to 0.016 meter. When object is here, what is your speed, right? Okay, well, let's use the energy conservation. When object is here at this location, you only have potential energy, right? Potential energy equal to 1/2 Ka squared, right? So we know A here equal to 0.032 meter. When object reach here, equal to 1/2 mv squared plus 1/2 k x squared, right? So this x equal to 0.016 meter. So plug everything in. you have half. Well, before that let's cancel all the half, right? So Ka square, K 26, A 0.032 square equal to M 0.4 V square plus K 26 0.016 square. Okay, to solve this equation, one unknown, find V. All right, that's number 7. Okay, number 8. 3.55 G bullet. So mass equal to 3.55 G equal to 3.55 10 to the power negative 3 kg. All right, embeds itself in a, okay, so embeds itself in a block. Okay, so we call this M1, this is M2. M2 equal to 1.47 kg, which is attached to a spring of a force. Okay, so K equal to 825 Newton meter. If the maximum compression of the spring is, okay, so maximum compression, right? So basically you have a bullet here and you have a block, then they will move together, right, to compress the spring. So move this way, compress the spring. And you can compress spring, maximum compressed spring is, we call this A, 5.88 centimeter, okay, 0.0588 meter, okay. Find the initial speed of the bullet. Okay, so what happened here is, so basically, there's a bullet. This is a block, okay, attached to spring, right? And then bullet, so ask you with V1, okay? So the bullet will hit the block, right? So bullet, initial velocity of the bullet is V1, and then hit the block. So this is a collision problem. And then this is the before, this is the before, this is after. Bullet and the block move together with the velocity VF. Okay, right? And then they move together to compress the spring, all right, to make the spring this much compression. Okay, so we look at energy conservation. We need to figure out VF first. So basically, bullet and the block together move together to compress this spring. So before it's compressing the spring, total energy here is kinetic energy, right? 1/2 m1 plus m2 VF squared. Okay, and then fully compressed spring, so velocity became 0. Now equal to, this is the kinetic energy of the block and the bullet. Turn to 1/2 K A square. A is like a maximum displacement of the spring. All right, so from this equation, half cancelled, right? And you can figure out the VF. Ka squared divided by m1 plus m2 square root. Okay, so you can, make the calculation, figure out what is the VF. And then after you figure out VF, right, then we go back to this scenario, right? So this is a collision problem. When you have a collision, you always have momentum conservation. So this is m1, m2, right? Momentum conservation. So m1 v1, that's total momentum before bullet hit the block. And then after bullet hit the block, momentum here is m1 plus m2 vf. You see, that's the momentum conservation. Momentum before collision, momentum after collision. Okay, so because we get a VF from this equation, then we can plug here. We can figure out what is V1. V1 equal to M1 plus M2 divided by M1. And then VF is this one, right? So square root of K M1 plus M2 and A squared. And you can take A out. Okay? Right? So this is the velocity before initial velocity of the bullet. B, the time for the bullet block system to come to rest. Okay, so now you start from here, right? So compress. So this is your bullet system, right? So you compress the spring, right? And then you make the spring stop. So basically, once bullet and block start to move, right? So you see you go here, compress the spring, right? And then go back, and then go here, and then you have oscillation. Okay, so if you have oscillation, you can tell, right? You start with the maximum, you have zero displacement, right? Now the spring have zero displacement, right? And then compress, and then come back, right? Then back to this location, right? If it's attached, you don't want to let them move away. You don't let this whole block move away, right? Then come back. Okay, you see? Well, this is your diagram, right? You see? So this is when you are here, right? Negative maximum displacement. You have zero velocity, which means you stopped. So this is one period, right? This is one period. 1/4 of period you stopped, right? Okay, so we know for this system, mass is M1 plus M2. K is, you have K, right? The period, 2 pi over omega, right? Equal to 2 pi M1 plus M2 over K. You see, we know omega equal to K over M, right? That's omega. So you flip it, M1 plus M2K. So this is the period of the oscillation of this system. Okay, when bullet hit the block, compress spring, right? Then you back and forth. So this is a period, and take about 1/4 of period for the block to stop. You see, ask you the time for the block system come to rest. It take you about 1/4 of the period, then it bring to from bring to stop. Well, it won't stop there forever, right? It won't stop here forever. Then after you reach a stop, then you move back. Okay, so you have oscillation. All right. So that is this problem. Let's look at next one. Next one is this, a simple pendulum of length. Okay, so now we talk about simple pendulum length equal to 2.3 meter. Make a 50 complete swing in 37 seconds. Okay, what is the acceleration of the gravity at the location of the pendulum? All right, so for the pendulum, we know that period equal to 2 pi L over G. Okay, and they ask you this question asks you about the G, right? So let's see. We square on both ends, T square equal to 4 pi square L over G, right? So G equal to 4 pi square L T square, right? So basically, in order to figure out G, you have to figure out T square and L, right? So we know L, this is L. And how to figure out period? Well, this one we get period from this equation. So you see, make 5 complete swings in 37 seconds. Period defined as time to finish one swing, one complete swing, right? So the period equal to, well, 5 swings is 37 seconds. One swing, right? So this is a period. Okay, so this is a period, whatever seconds, right? So basically this is a 7.4 seconds. And then you just plug in period here and the length here, and then, you know, everything. Then you get the gravitational acceleration at that location. Okay. Number 10. A fireman tosses his 0.98 kg hat onto a peg, where it oscillates as a physical pendulum, as shown in the figure. If the center of mass of the hat is 8.4 centimeter, so we know this case L equal to 0.084 meter from the pivot point, and its period of the oscillation, so t equal to 0.73 seconds. What is the moment of inertia of the hat about the pivot point? Ask you moment inertia. Okay, so how to solve this kind of problem? Basically, this is a physical pendulum, right? For the physical pendulum, you see this is your pivot point. Assume this is your center of mass. Okay, so this is the center of mass. It's a cm, right? So you swing back and forth. You see, you have this is your object center of mass, right? And then this is L. Okay, and if you do a free body diagram, right? So this is your, this one have a mass mg, okay? And the net torque, right, equal to mg, okay? And then L, and then sine theta. If the theta is small, angle is small, equal to mg L theta, right? Small angle approximation. And also this is negative, right? Negative, right? Equal to k, negative k theta, right? So it's proportional to, well, this k, we call it k prime. Okay, it's kind of the same, similar to spring constant, but it's not, right? So which means, so torque proportional to angular displacement. All right, so if that happens, then we know that angular frequency equal to square root of k prime over moment of inertia, because this is rotational motion. Okay, so this is equal to, you see, this is k mg L I, right? Okay, and then we know period equal to 2 pi over omega equal to 2 pi I mg L, right? And then we know from the question, we know this is 0.73 seconds, right? So we know M, we know G, we know L, right? So M, L, and G is gravitational acceleration, 9.81. In general, use this value, right? Then from this equation, you figure out moment of inertia I. Okay, so square on both ends, right? Square, so 4 pi square I mgl equal to 0.73 square, right? Then you just like move everything to other side equation, right? So I equal to 0.7 square mgl divided by 4 pi square, okay? Then you substitute mgl into this equation. That is moment inertial. Remember, moment inertial always kg meter square. That is the unit. Okay, so kg meter square. All right. So that's all for the homework of chapter 13.